last talk in the session is Patrick about type-guided repair.
Okay, hello. My name is Patrick LaFontaine, and I'll be presenting our work on type-guided repair of incomplete input generators. So I think we would all like our code to have less bugs in it, but unfortunately, we do not necessarily write enough tests to exercise all of these bugs. So one alternative is to use probability-based testing. It's an automated testing strategy. It comes in a variety of frameworks in basically all of your favorite languages. So as our motivating example here, I have an OCaml function in QCheck, which is going to be testing one of our functions, and it has an interesting size list precondition. So what do you start out with? You're going to need some kind of generator. So most of these frameworks come either with a built-in generator, or you can use a macro annotation on your data type to produce a lot of random values of that data type. And then the next part of our step is to take that data and pass it into the user-provided precondition. So this is the precondition to the user's function under test. So if your data does not satisfy this precondition, you're going to have to generate some new data. And here is our precondition, which is lists of some bounded integers length. So then we have the user's function in our test, of course, which we provided our input to. And then we will check the output of that function against a user-provided postcondition. And if this ever returns false, then we know we found a bug. And otherwise, we iterate for some large finite number of steps to look for one, continue looking for one. The focus of this talk is going to be on this inner loop here. This is where we are doing work on generating data that is not satisfying the precondition, and so we're not actually making any forward progress in testing the user's code. So there's a question of like, how well does this default generator do? So we have our default generator for lists, and we have our size list precondition. And we find that in this case, only about 50% of the lists that we generated are valid. And that sounds okay, but as you start to have more restrictive preconditions, you're going to start to reject a lot more inputs. So now the rest of this talk, we're going to use our motivating example of a precondition around even lists. And we find that this rejects 90% of the lists that are generated. So only about 10% of lists are actually valid. So one thing users can do is that they can go and write specialized generators. These are generators that they ensure only will produce data that is valid for their precondition. And of course, we find that these generators produce only valid data. One of the problems is that users actually have to go and write these specialized generators to actually ensure that they have the properties they're interested in. And additionally, if you have multiple, for every new test that has some different precondition, you're going to have to write some different generator. So, but still, like we've taken our problem before and we've reduced the problem from who wants to write tests to who wants to write test input generators. And this is not just a meme. User studies have found that developers do not want to do this. They would much rather just use the derived generators whenever possible. Okay, so this looks like a good opportunity for program synthesis, actually. And let's look into that a little bit. So program synthesis requires a specification of some kind. So here I'm going to start with just a high-level specification, which says that our even list generator should only produce non-empty lists containing the even integers. And then additionally, you're going to need some structure. So here, we're going to use a set of components and then an initial template to work off of. This is a very standard template for probability-based testing because generally speaking, you want all your generators to be sized and to have a finite number of steps for their recursion. But if you apply most of your traditional program synthesis techniques, what you might get is a very unsatisfying generator like this. This is a generator that no matter when you run it, will always produce a singleton list containing 0. But I would like to note that this generator does satisfy the initial preconditions we proposed, which is that it only produces non-empty lists of even integers. In contrast, a better specification would be one that says that our even list generator produces every possible non-empty list containing the even integers. And this is what we would call as a good generator because it gets a sufficient set of the values you'd expect. So what is our missing ingredient here? Our missing ingredient is actually coverage. So when I've been talking about every here, I've been talking about some past work by my collaborators on coverage types. This is a coverage type specification up here. And what we're trying to define is these generators that can produce every possible value that our users might be interested in. So formally, before when I was saying, like I was using words like only and every, only corresponded to our, like a traditional safety property, and every corresponds to a coverage property. To give you a little bit of intuition for how these coverage types work, if we imagine our generator as producing a set of outputs, then our safety properties are over-approximate. So they set an upper bound on the set of all values that can be produced, but they don't necessarily tell you where inside of this larger set are the values that you're actually producing. In contrast, coverage is an under-approximate property. So in this case, it sets a lower bound on the set of values that can be produced. And then you could potentially go over, but it necessitates that you must produce at least this set of values. So the rest of this talk, I'm going to be presenting my work on Cobb. Cobb is combining work on coverage type verification, which are these coverage types, and taking some ideas from the type-based synthesis world according to safety, and bringing these together in quite a nice form for product-based testing. Okay, so how does Cobb work? Cobb, in a nutshell, is two phases. The first phase is going to be identifying the set of missing coverage from our either incomplete generator or from the initial template we get. So we identify the set of missing coverage that we can abduce, and then we're going to take that missing coverage and we're going to localize it to a series of typed holes to create a typed sketch. From that, we can then proceed to do an enumeration where we will enumerate sets of terms until we can find terms that satisfy each of our holes, and we can use them to repair our sketch until we get a complete generator. So I don't have enough time to talk too much in detail about our first phase, but I'm just going to walk you through our motivating example. So the input to our first phase is, of course, our coverage type specification as we have before, and we have our incomplete generator. And through our two different steps, we will arrive at this typed sketch. So this is a sketch with a series of typed holes in it. Each of our typed holes has a corresponding typing context, and we've pushed in all of our missing coverage that we're going to be looking for. Okay, so given our typed sketch with these typed holes and our coverage type specification, we can now proceed with the synthesis process. Okay, so synthesis, we're going to be applying a bottom-up cost-based enumeration. And our goal here is to continue iterating until we can exhaust the space and find the set of repairs, or you hit some upper bound, or you hit some timeout. So our first step is to choose one of the holes. And remember, one of these holes, they come with a corresponding typing context, a set of local variables, which is going along the paths to that hole, and then the missing coverage that we're looking for. And I mentioned that we're doing bottom-up, so we're going to start from a series of variables and constants, and we're going to start combining them together with our components. And this is how we're going to proceed with our enumeration. Each of these terms is going to be, we're going to run type inference on each of these terms with relation to the corresponding typing context of that hole. We're going to use this to infer a coverage type for each of them. And then we can perform type checking and checking for equivalence. So we can look at the coverage type of the type we just inferred. We can compare it to other similar coverage types to see that we actually have a unique set of coverage for each of our terms. And we can throw out ones that are not unique. Okay, and then so for each of these terms, we can also keep checking them against the missing coverage that we're looking for in our typed hole. And this is just a subtyping check. So we can do a nice little subtyping relation. And for our initial set of terms, these do not help us with our missing coverage, but that's okay. We'll hold on to them, and we will use them to help enumerate some larger terms. So as we go, we're going to start to create some more complex terms. Especially, we like to prioritize recursion, because it often will create shapes of coverage that are well aligned with what we're looking for. So here's a couple examples of some terms you might start to enumerate. And as we go, this is where we will start to prune out some terms. So one of our terms we're going to prune out for safety reasons. So if you recall, if you make a recursive call with intgen, that is any possible integer. This violates our structurally decreasing recursion property, which would be very bad. Your generator would never terminate. So we will prune this out as being unsafe. And likewise, if you, in this case, we call evenless generator with 0. So that would just be equivalent to our base case, which is a term you might have already enumerated by now. So this would be equivalent to a coverage to this other term. So we can prune that one out as well. So we can keep going. We can start to enumerate even larger and more complex terms. We can run type inference. We'll check. We'll do the normal type checking and equivalence check, the uniqueness checking. And in this case, when we compare the inferred types of these terms with our missing coverage, we find that our subtyping check succeeds. That means that these terms could potentially be useful in repairing of the holes. So we'll proceed to that now. So how do we actually do the repair? So as we've been inferring the types for each of these terms, we've been building a subtyping lattice. This is a lattice where our partial order is on the subtyping relation, and we've been putting useful terms into this lattice. So here's an example of what this might look at this point. Then what we're going to do is we're going to insert our typed hole into the subtyping lattice. And this leads to one of two things. Either we immediately find a term that is equivalent to our typed hole, in which case, great, we're done. Otherwise, we can perform a lattice join. So we can look at amongst the children of our typed hole, and we can see if the coverage of all the children of this typed hole is sufficient to cover the full set of missing coverage. In that case, we know we're going to have a solution, and we can prune out any unnecessary terms and get a nice repair. Otherwise, you'd keep going. Okay, that was cool and all, but let's talk about some numbers. So I've implemented Cobb in OCaml. It's about 4,500 lines. I want to have Cobb be able to reason about a variety of different data types, so lists, trees, redback trees, and the lambda calculus. Additionally, we want to be able to use a variety of different properties, so different kinds of size lists and trees, different kind of data constraints, so sortedness, uniqueness, and duplicates, variety of different validity constraints around BSTs and redback trees, and then of course well-typedness for the simplicity lambda calculus. And then for each of the kind of holes that we want to repair, we want to have a variety of different branch conditions and local variables. So what I've done is I've gone into the literature for a variety of the different generators, and I've taken them and I've made them incomplete by removing different terms from them. And in our most general case, this would be like, in our initial example, we had that very loose template that we use for even list. This would be our most general form, where there's only a little bit of control flow, and then there's no actual coverage being provided from the template. So one of our results is that Cobb is actually pretty fast. So when we look at our most emptiest template, we find that Cobb, in general, finds the most precise coverage in about under a minute for a variety of our different benchmarks. And additionally, when we try and compare Cobb against other forms of repair strategies, because as I mentioned, Cobb is taking into account both coverage and safety, we might want to ask, what if you just did one or the other, right? So for here I'm talking about the coverage only repair. So if you only wanted to repair for just getting a good set of outputs, you could use the default generator. So in this case, the default list generator. That would always be a valid repair. So this would help you get a coverage complete generator. However, now your generator is going to start to produce a lot of invalid terms. And we characterize this by running all the different the Cobb generator and all the different variations for 20,000 outputs. And we track how many of the 20,000 are actually valid. And as you can see, in the worst case, in your sketch variation, only about 2,000 are valid, so about 10%. So there's a whole bunch of other stuff in the paper, which I'm not going to be able to talk about. We, of course, evaluate on the simply type lambda calculus. We have a whole bunch of more numbers and analyses that you can see. We compare against the safety repair strategy. We looked at dynamic constraint solving. So if you had a constraint solver at runtime trying to find valid and unique terms, this is rather slow. We also look at how Cobb performs when on perturbations of the components, and we have a soundness theorem. So in conclusion, users don't want to write input generators, and our solution is this coverage type guide to repair. We have an initial phase where we find the missing coverage, and we have a second phase where we actually do the repair, and we synthesize some terms. And Cobb is an efficient one-time synthesis process for this task. Thank you. I'm happy to take any questions.
We have time for a question or two.
Or you can find me on lunch.
Hello, as you mentioned, thank you for the great talk. As you mentioned, the lambda calculus as a simply type lambda calculus as your example. How do you deal with the mutually dependent specification? Like in case of lambda calculus, there is normal form and neutral form. If you want to generate the normal form only, then you need to depend on normal form and neutral form to generate that kind of specification. So I'm wondering, how do you actually deal with the mutual recursion in case of there is a mutual recursive specification for the generated input, generated output, generated test cases.
So the simply type lambda calculus generator that we use is from some past work. So I believe this generator is probably a little bit simpler. So it doesn't have this, we don't have to synthesize two functions at the same time. So in our case, we do have a bunch of recursion, but it's not like flipping back and forth. So maybe that would be a more complex generator we could look into. It's kind of interesting to think about how you do multiple synthesis tasks at the same time.
Okay. Thank you for the answer.
Thank you.
Take the last question over lunch, just out of fairness. Thanks very much, Patrick.
Yep.